Good evening, everyone. Centax, facilitated by Global. Good evening, everyone. Centax, facilitated by Global Facilitators, aims to offer extensive exposure to Centa teachers community, focusing on their optimal classroom practices and professional development. Therefore, we anticipate your active registration for these sessions, wholehearted participation by sharing your insights, engaging in polls, posing questions, and more importantly, providing critical feedbacks to enhance the session. Now I'm giving a brief introduction on the process. Well, welcome to Centa webinar series for teachers. We are delighted to have you all here. I hope everyone is feeling excited and ready to dive into today's topic. The topic for today's webinar is hands-on experiments in science classrooms. And the facilitator for this session is Mr. Sharit Sharma. Welcome, sir. Mr. Sharit is a co-founder of Avinshka, a center for science, maths, arts and technology dedicated to revolutionize science and math education. Avinshka aims to make learning engaging and effective through hands-on experiences such as model experiments and projects. At Avinshka, teacher became storyteller using experiments and model as props to make STEM education accessible to everyone, regardless of their social economic backgrounds. With a, with a passion for technology and science education, Mr. Sharit holds a PhD in electrical engineering, electromagnetics from Iowa State University, USA. His extensive knowledge and experiences are evidented by numerous publications and patents. Outside of his professional accomplishments, Mr. Sharit enjoys working with local communities, setting up libraries, and creating joyful learning experiences. His innovative approach to teaching, along with his interest in designing bamboo furnitures and organizing spaces, highlights his commitments to making learning both enjoyable and impactful. Welcome again, sir. Before I hand over the session to the facilitator, I would like to inform all teachers that they will receive participation certificate for this session. So please do fill out the feedback forms. From that we will be able to share with you towards the end of the session.
Hello, everybody. Just curious about how many people do we have in the audience? Okay, thank you. Right. So we are supposed to be talking. Oh, we're supposed to be talking about hands on science, right? So usually we try to do sessions sometimes so that everybody can understand, right? But that's not always the case. ठीक है? जब हम लोग चाहते हैं कि सबको समझ में आए, तब हम लोग अक्सर हिंदी में करते हैं, है ना? और जब हम चाहते हैं कि थोड़ा कम समझ में आए, तो अंग्रेजी में करते हैं। और जब हम फिर भी देखते हैं कि लोगों को समझ में आ रहा है, तब हम लोग जापानी में करते हैं। ठीक है? और जापानी के आगे भी हमारे पास हल सॉल्यूशन है। अगर वो भी आपको समझ में आएगा तो हम लोग फिर एस्पेरांटो में करेंगे। ठीक है? हम देख सकते हैं आप लोग एस्पेरांटो क्या है। तो आज हम लोग खैर कोशिश करेंगे कि थोड़ा सा कम समझ में आए, तो इसलिए हम लोग अंग्रेजी में करेंगे। लेवल 2 पे हैं हम आज। ठीक है? तो वी आर गोइंग टू टॉक अबाउट हैंड्स ऑन साइंस एंड आई एम गोइंग टू ब्रेक दिस इनटू 2, एक हैंड्स ऑन और एक साइंस। हैंड्स ऑन वो जो मैं करके देखूं। हैंड्स ऑन इज समथिंग दैट आई एम गोइंग टू फिजिकली डू समथिंग That's hands-on, right? It could be anything. I could be a hands-on musician, but then I know many hands-off musicians also, right? But then there is science. So we are going to do things using our hands and stuff to figure out science, right? And what do we expect today? I think what we are expecting is that how science is done using hands-on methods and discovering things for ourselves, answering our own questions, which is called the method of inquiry. That is going to be our goal. I will. What was that? Sorry. Oh, I will also be asking the questions and I will also be answering the questions. Right? This is a disclaimer. So, but in a classroom setting, you need not necessarily do that. You may want to ask questions and you may want your students to answer the questions, or even better, you can ask them to come up with questions. That is the best that you can do. Okay, just this. Let's talk about science. What do we think is science? It would have been nice if it was a live audience and we could, really ask what does everybody think about science. And I'm sure we get lots of answers. And I will, to keep the time constraint in mind, I'm going to just say that science for us, what it is to understand the world around us. That's our goal. And there can be many ways of understanding the world, experiencing the world, knowing the world around us, right? This is one of them. And what's so special about this method of science? The special thing is that it will be based on evidence, logic, and data. That's the special part, right? I can be a painter and I can experience the world through colors, but it doesn't have to be based on evidence, data, and logic. It's emotional, right? And that's a good way of knowing the world, experiencing the world. But this is a world where we are going to use this, right? And when I'm saying to understand the world around us, let me just write this and see how that will make sense to you. We have heard what is known as science, and then I'm going to change this to political science. And we have social science, right? We have life science, we have geoscience, and so on. Right? So, science is the way to understand the world around us, but which world? That's defined by the first term. Then science becomes the adjective here. That is it the world of the society? Is it the world of the politics? Is it the world of the life? Whichever world you choose. And the method should be based on evidence, logic, and data. So hold me accountable to that. Okay? Hold me accountable to that. So we are trying to understand the world around us. So let me write world. What do you see around yourself? What fills my experience of life? How do I experience the world? What's around me? If you ask me right now, I'll say, oh, there's a glass of water. Oh, there's spectacles. There's this little sheet of paper. There's pen, table. Maybe there's a few people around here. Oh, so what is this? This stuff that we label, right? I'm going to give it a name, and we call them things. What is so special about things? How do I know that it is a thing and not a non-thing? Right? It occupies space. things occupy space. They cannot be zero in measurement when you measure the length, width, or dimension, any other dimension. Okay? Then there is stuff in my life which is not things. Like I sleep, I laugh, I cry, the water falls. So these are not things, but this is something happening to things. So the key word is happen, and they are called events. How do I know that it's an event and not a thing? Because the event will occupy time. Most of the time, you can even think of events as changes that happen to things. That's a very interesting way of looking at it, right? So I have things, and then I have changes to things, whatever change it may be. It may be change of temperature, it may be change of color, it may be change of size, change of location, right? So where do we live now? We live in space-time. We're surrounded by what is known as space and what is known as time. Now, we're going to talk about today, what we're going to do is, of all this stuff, we'll talk about things. So I'll just get rid of everything else. So we live in a world, things and events, and out of that we have chosen things and many kinds of things, and we can classify things in many different ways. What I'm going to do is, I've chosen a very specific topic today. I'm going to talk about water. So what the name I have given to this is Pani Ki Kahani. Okay, we'll talk about water. So let's try to figure out what we already know about water. There are many things about water, right? First thing that comes to mind is what? That's it's essential for life. Okay, and it is, some people might even use some jargon and call it liquid, whatever that means. Then what else do we know about water? Can we talk about its color? Or maybe the absence of color? Can we talk about its smell? What about the weight? Oh, it has weight. Water has weight. What does that mean, water has weight? That means if I leave water in the middle of nowhere, it will fall down. That's everyday experience. Right? So it has weight. So I have a lot of things about water. I am going to now do some so-called hands-on stuff, right? So that I can figure out more about this water. So I'm going to make a little change here. Yeah. So I have some water in this glass and kind of half full. Oh, I see. Some people are already disagreeing with me. They are saying it is half empty. Oh, that's good to know that we can both be right and use entirely different language. I'm going to take some of this water and pour it out. So there was water in one container, and now it is present in two places. So water can be, what can I write from my experience? What have I done? I'll get rid of this also. I like a clean board. And I split it. I can use the word broke it, separated it into parts. So when I separate it into parts, what I get is, when I split it, I get parts. Okay. Can I split this further? Oh, you bet I can, right? Here you go. Now, it's in 3 parts. How many parts can I split water in? Well, my first answer is as many as I want. That's my first shot. Oh, maybe infinite number of parts. So that means water can be split into parts. And when you make them smaller and smaller, we just call them particles. So if you look from this side, what I'm saying is that water can be split into parts, into smaller parts called particles. How about looking from this side? That particles come together to make water. So water is made up of particles. I hope we are in agreement that it makes sense to say that water can be split into parts. So I am making the statement that water is composed of parts or particles. What about these particles? What about their behavior? Okay, so I'm going to start with this. I'm going to use my finger, and now my finger is wet. Let me write that. Finger is wet. Now we'll go to the dictionary and try to figure out what it means when you say something is wet. What does it mean? That there are water parts or particles all around my finger. Right? So, and what are they doing? Why are they around my finger? It looks like they are sticking to my fingers. Right? So when water sticks to my finger, I say what my finger is wet. But how about a stick? There's a wooden. Now this is wet. So water sticks to a wooden piece. And what else? I have a spoon here, and if I put it in, oh, this is wet too. And what else? I have a piece of cloth here. If I put it in, it's wet. So water sticks to things. Water is, so one, I discovered that water can be split into parts. Second, water or water parts or particles, they stick. So they split and they stick. So they are splitty and they are sticky. You might as well say that, right? Is there anything that the water will not stick to? Maybe more or less, right? Sometimes more, sometimes less, but I think water is sticky. Let me, I have a little foam block here, right? Now I'm trying to stick it to this board. Let me try it again. Whoop. Okay, now I'm going to put a little water to it. How? Water is sticky. Okay? I'm trying to convince myself, and in the process, hopefully, I'm trying to convince you that water is sticky. Okay, now I'm going to continue with this. I'd put my finger in here and it had gotten wet. Now my finger seems a little less wet, almost dry, but where is the water? Oh, right here. It's sticking to a cloth. So that means it sticks more to the cloth than to my finger. Okay, so nobody said that it's equally sticky to everything. No, but it is sticky. Let me try one more thing. Okay. Hmm. I don't know if you can get the video of this, but I'm going to pour some water here. First, one. And the first thing I notice is that most of the water sort of bunch. So not only is water sticky, but it looks like it is sticky to itself as well. Now I'm going to put my finger here and see if you can get this or not. And I'm going to try to pull it up. Can you see what is happening? Is it possible to see that? Do you see what is happening? I'm able to lift water up through my finger. I hope you could see it. If not, I have more stuff coming. Okay? I can even move this water around. You know what? In this plate. See? And most of it will try to stick together. So water is sticky to others and water is sticky to itself. Now let me try another thing. I have a dropper here. There is a little drop of water coming out. Do you see that? Is that visible? And it is right hanging there, just before falling down. If it is not falling, I'm talking about that. Okay? So now I'm going to draw a picture of this. And let's see what sense I can make out of it. Right? There is this dropper. And there is this water drop sticking out like this. Right? Now I'm going to trying to figure out that why this water drop doesn't fall down. So number one, immediately what comes to me, it is sticking to the dropper because it is sticky. We've already done that. Now let me think of this water drop. I know that water can be split into parts or it is made up of very, very small parts. So it must be made up of a part here. And what is holding this part at the bottom? What's holding that water? The only thing that can hold that little piece of water is the piece above it. So it must be sticking to this piece. And what about this piece? It is being held by the piece above. And this is being held by the piece above, and so on. And over here, this piece is being held by the dropper. And the dropper itself is being probably being held by my hand. So ultimately, yes, I am holding this drop up, but in the process, what I have discovered is that different layers of water within that drop are actually holding on to each other. And how do I know that? One, I have already made a conclusion that water is made up of small parts and particles. How many? Lots of them, right? So I have just drawn layers, but actually I could have drawn little even smaller parts. And what are all these parts doing? They are all holding on to each other. And that's why you see that it is present as a blob, right? So water particles are sticky in two ways. I'm going to classify. Okay. Now, for those of us who are a little jargon happy, we're going to put some, and let me before do that, let me put another one. That water has. Okay, let me just say that if I just tilt this glass, and water is falling down, right? And I'm not pushing it down. I am pushing it out of the glass maybe, but I'm not pushing it down, but it goes down, and which means it is being attracted to the earth. So earth attracts water. Attracts water, and we call it gravity. Now we can start getting a little happy about our usual words of science, right? We call it gravity. And when it is sticky to itself, it is called cohesion. And when it sticks to others, it is called adhesion. Right? So we have three new words here. Cohesion, adhesion, and maybe gravity is not so new. Right? So if I was to look at a piece of water, a particle of water in the middle of nowhere, or maybe in the middle of somewhere, actually, it is going to be surrounded by some stuff or by water, so it's going to get pulled, right? It's sticky, so it wants to stick to others, or it wants to stick to self, or it wants to go down because of gravity, because of weight. I'll just put that as okay. Now let's see if this explains a few more things for us. Okay. I'm trying to pour some water into my hand, and let's see if I'm trying to drink it. I do pour some water like this and see where it goes. Do you see where the water is going? It's coming out of my elbow, right? So what do you think is happening? What do you think is happening? The water is trying to go down because of number 3, and but it is not going down straight. It starts to move to the side and tries to stick to my hand because water is sticky to others. But just saying sticky is also good enough, actually, right? So it is, in other words, for jargon happy people, it is adhesion, right? And things which stick to others in the market are sold under the name of adhesive. Not a surprise. Okay. What else do I have here? Watching my time. Okay. Maybe we have done some kind of understanding of water. Again, I'll just repeat what we just did. Water can be split into parts, so it's made up of particles, composed of small parts, you can say that, and water particles are sticky. They stick to themselves and they also stick to other things. And if I throw water out, it won't stay in the air as it is. It will come down. That's what it means. And I don't know why, but that's my experience. That is what I know happens. Okay. Oh, one thing I didn't write in the beginning, in the properties of water was, what is the shape of water? Choices? Do we have the poll up? So, I can't see it. So maybe somebody can tell me what are the choices there. Online? Yeah. So yeah, what does the poll say? Oh, sorry. Oh, what does the poll say now? Tell me.
44% says take the shape of the container.
Mm-hmm.
25 and 25, no shape or no fixed shape.
No shape or no fixed shape. Okay. Did you have an option like I don't know types also?
None of the above.
None of the above. You did.
3%.
Oh, only 3%. Oh, interesting. Okay. So I'm going to remove all of this actually for right now because I think we have absorbed the gist of it. Okay. So we are just talking about the shape. So my everyday experience that water takes the shape of the container, right? Let me bring up a container. Oh, it takes the shape of the container. Now let me tell you what is the shape of the container. The shape of the container is this. And where is the water? It's here. So first I want to tell you that it is not taking the shape of the container because the shape of the container is up to here. This is the full shape. So it doesn't take the full shape. What if it was to take the shape of the container, it should have filled up my glass like gas would do. Gas would fill up a container, but this doesn't fill the container. So it's not taking exactly the shape of my container. There's more to it, right? It is filling only the lower half or the lower part of the shape of the container. And why would that be the case? Why is this water not jumping up and taking the shape of the container? It's just sitting there at the bottom. Why? Because it has weight. Because somebody is pulling it down. So that means it has this shape. It is taking the shape of the container bottom half because something is pulling it down. Let me try to put a drop of water just in the middle of this and see what happens, right? Oh, I'll put it on the right on the table actually. Let me put, now there is no container. There's no container. Container necessarily means which contains. That means stops you from spreading around, right? There's nothing stopping it from spreading around. But yet it seems to have a shape. So it is not no shape. It has some shape. Which is what? Which is more like a blob. If I was to draw it, top view, it looks something like this. Not even like this. Maybe something like that. Yeah. Looks like it's something like a blob, right? Roundish, if I can say that. Roundish is the word I'm going to use. Right? Let's think about what would water look like if I was to switch off gravity. No gravity. I'm going to remove this weight. That means water had no weight. There was no reason for water to move downwards. There was no reason for water to move upwards either or sideways either. There was no reason for water to move in any direction because nobody is pulling it. I've just switched off the gravity. So what shape would water take? We know the properties of water. What do water is made up of? Small particles. So let me just draw those particles randomly, wherever. Now let's think about it. Random particles. And now I am saying that I am going to try to figure out what the shape will be. What is the property of these particles? What particles do? They want to stick to each other. That means what will they do? These particles, will they stay as far from each other as possible? No. They will come close and close and close. Then what will it look like? If they all came closer to each other, what would they look like? What shape would they form? Something like this. They all come together. Why? Because they want to stick to each other. They attract each other. I have already figured that out. Right? So this is in 2 dimensions. What would you think water would look like in 3 dimensions? Same thing in 3 dimensions. And what do we call it? We call it a sphere. It looked like a ball. That is the shape of the water, right? So some people said that why should we believe it? Of course we should not believe it. So I'm going to show you some hands-on experiments. This is when I was traveling to the International Space Station. That is the time when I had my cell phone with me and I took a small film, right? And I'm going to share it with you. So in International Space Station, there is gravity, but you cannot experience the effect of gravity. Experience, right? The gravity. For now, just take that for granted that that is how things work. So let's take a look at our video. Space station. Yeah, please. Are we ready? Nozzle, and then the water comes out, and then it will take whatever shape it wants to take. When nobody is pushing it and nobody is pulling it. What is the natural shape of water? Are we there yet? Oh, okay. So let me know when you're done. Oh. Can you hear me? What does it mean? Oh, you mean through your phone? Okay, okay. So, okay, here. Can you see this glass? It's a plastic glass, right? If I was to ask you, what is the shape of the rim, right? You will say it is circular. But look at it now. Oh, it's not circular anymore. What happened? Because I'm pushing it, I'm pressing it, right? So that means the shape of the objects can change by what we do to it from outside. So the shape of the water in this glass, of course, it takes the shape of the container, but only because the earth is pulling it. Otherwise, it is a sphere, right? And have we ever noted that in our everyday life, we don't come across spherical things? We don't see anything spherical. Has anybody seen anything which is spherical naturally? No? Maybe. Oh, look up in the sky. Maybe you can see some things which are spherical. The moon, the sun. Oh, maybe our earth is spherical too. We have been told, at least. I have not seen it firsthand, but I have been told. And maybe the stars are spherical too. Why would they be spherical? Now that I know what the natural shape of water is, and I'm going to extend that a little bit and say that what is the natural shape of liquids? It's a sphere. When nobody else is pushing or pulling it from outside, then it is a sphere. But so what is my guess? What about the moon and the earth and other objects? Why are they spherical? At some point, they were all molten. They were all liquidy. They were all water-like. And that is why they took the shape which liquids or water naturally take. Okay. Now I'm going to do one more little so-called hands-on activity, because this is a hands-on show. And I hope I can convince you about some of the funny things that we are doing here. This is a coin, and I'm going to place the coin on this little wooden block, and I'm going to use a dropper, and like this, let me clean it up. Okay, I'm going to show you what I'm going to do on it. I'm going to put drops of water on it, like this, and I'm going to go on adding some drops to it. So before I proceed, I want you to make a guess. How many drops of water can I throw out of my dropper onto this coin, and they don't spill off the coin? They remain on the coin itself. They don't come out of the coin. Okay? So I would like the poll to come up, please. If we can have the poll, please. You have to make a guess, an estimate, a judgment as to how many drops you think. Maybe you add a little angle. Yeah. Do we have the poll or not yet? Oh, okay. Okay. So we have a bunch of guesses. I'm hoping to see more. Oh, somebody's made a very big guess. Oh, some people are dreaming here. At least if they are dreaming, I hope they are not sleeping. Right? Okay. So again, this is hands-on, right? So why don't we do it and see? So why don't I keep adding drops and you keep guessing? Okay, one, so is already done. So now it is 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So our 5 to 6 guessers are out. You're already out of the game. So I've done 10. Somebody says 5 more. So that means you're saying 15. Okay. So we've done 10. 20. Okay. Now I think the people who are dreaming are not looking like so much like dreamers anymore to me. It looks like they may be onto something. Let me try a few more drops. Okay. So 10. Okay. Now 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Any more guesses here? We already have 20 drops on the coin. Any takers? Yeah? 15? We have already done 20 drops. So you can't guess. Somebody says 810 drops. Is that right? Am I reading it correctly? Oh, 8 to 10. Okay, that's not 810. Okay. Okay, somebody has given the answers for the poll. Oh, okay. So now we are up to 20. Now, oh, some people are guessing 40 and all. Okay, now let me try some more. So this is going to be 21, 22, 23, 24, 25, 26, 27, 28, 29. Oh, 29. We could do only 29. Not bad, huh? So what do you think is holding these drops of water together on top of this coin? Right? So let me draw a picture just to summarize the whole thing. This is the coin, and I was pouring water drops. So what happened is the drops formed a blob like this, and they were not falling off. Or maybe I should draw an even better blob. Towards the end, when we had around 30, maybe they were like, oh, it was bulging on all sides, and yet holding on, right? So what does it tell me? That water particles absolutely hold on to each other. So we should not be surprised that they form a globe, they form a sphere. And so today what we have learned is why all my heavenly bodies are spherical, why the sun is a sphere, the moon is a sphere. And where did we start from? A very, very interesting TLM, which is this glass of water. Okay. So let me, so I'm pretty much done. You know, I would like to hear some of your comments about what you think we're doing here and how we are doing. And then I will try to summarize maybe a little bit. Any questions, comments, or anything? Okay. Yeah. If somebody wants to use the speaker, I think we would be okay. Or maybe not, maybe chat just, huh? Okay. Maybe I'll try to read some of your comments. Yes, Neeraj is saying every object wants to minimize their outer surface. That is a very cryptic thing, right? And I can't even prove it, that they want to minimize their surface area. Yeah, sounds good, I know. Really sounds good. Except I have no first-hand experience of my life which tells me that, right? I'm very much interested in my everyday life experience and doing stuff with things around my life and then figuring out their behavior and trying to extrapolate it to understand the larger things. Sometimes very smaller things too, right? We already talked about the water particles, right? Some people like to call them molecules. That's okay. You can call them whatever you want to call them, right? At our institute, we call them Chotu. We call them Chotu. So yeah, any questions too? We're happy to take. We do have a few minutes here, right? And maybe I'll just write down on the board what are my thoughts, or what I thought I was trying to do, or what I wanted to do. I'm not sure if I was so successful, but I think one, I was interested in the language. I wanted the language to be simple. I wanted the language to be understood by everyday folks, even those who don't do science. That's my goal here. Okay. And but I wanted to be correct. Simple does not mean that I can, get away with fudging things. No fudging. Okay. Then what I wanted to do was I wanted to keep it maybe local and inexpensive. Local and inexpensive stuff is what I'm using. So I'm using every things that are available to me very easily. Okay. And I'm trying to, in my language, I will, but explicitly put that here. Uh, Avoid using jargon. Or if I do use it, I will first define it, explain it, understand it, and then we will name it and label it, and so that it looks like jargon. That we understand the thing. Now, what do we call it? We'll give it a label later. We won't start with the label. Okay. And was there anything else I want?
Yes. There is a question.
Yeah, sure.
So sun is spherical, but it is not liquid. That is
Okay. Yeah. So today I did speak about liquid, but we only had so much time. We can extend this to what we call fluids. So gases will get included in that. Things which can flow, right? They will show the similar behavior. Gases will also show a spherical behavior if left to themselves.
And the other question is, what is the cause of this stickiness or attraction?
Oh, great. So I'm going to write that here. Please watch very closely. Watch very, very closely. I'm going to write the answer here. Okay? And this is a very valid answer. As a first shot, it's perfectly okay to, it's a wonderful question you have. And we should acknowledge that we don't know the answer. Can we figure out the answer? Absolutely. Are there ways? Are there other people who have figured it out? Yes, they have. Okay? Yes, they have. And maybe some other day, if Centa permits, time permits, right? Some other day. But as for now, I will just leave you with I don't know. And this is one of the most important statements that you can do in science. To be able to acknowledge what are the boundaries of what I know and what are the boundaries of what I don't.
Thank you, Sarit sir, for a very engaging and informative session for our community. I'm sure that our teachers have got a lot of takeaways from this session, like importance of hand-on learning, designing effective experiment using the easy to find materials, inquiry-based learning to help students ask questions, conduct experiments, collect data, and make discoveries, resource management tips for organizing the material effectively. If you have registered and filled the feedback forms for the session, do check your record of participants in the app in My Learning section. Thank you so much for all participants for engaging with us today. To register for more such upcoming webinars, please visit Centa app. Good night.
can say it now. Thank you, Subramaniam.
Thank you, sir.
Thank you, Subramaniam.